Good morning, class. So today we're going to be talking about molarity, and we're going to be looking at how that happens with two different chemicals. So we're going to have one that's an acid, one that's a base, and we're going to combine those and see how that looks. So this came up good because we were working on a pH experiment, and pH has a lot to do with molarity. And so the higher the molarity of something, if it's an acid or a base, that determines how strong it is. So we have our acid, which is going to be HCl, and we're going to see what the molarity of that would be. The higher the molarity of HCl, the more concentrated it is, and then the stronger acid it will be. So we're going to be combining HCl and NaOH, and that's going to be our overall reaction that we're going to be looking at. And this is going to be a double displacement reaction, so they're going to pretty much switch partners. So the H is going to go with the OH, and the Na is going to go with the Cl. So that your products end up being H2O and NaCl. So this is going to be our overall reaction that we're going to be doing. And we're going to be looking at molarity. So the formula for molarity is M equal to N, which is going to be our moles, which we've discussed already, over liters. And this has to be in liters for it to be molarity. So the molarity is equal to the moles over liters, which is your volume. So you have your moles over your volume, and that gives you your molarity. So to do that, we're going to go through an experiment, and we're going to be able to try to calculate the molarity for an unknown acid. So now we have our setup for our experiment in which we're going to see this reaction take place. So the way we're going to do this is that we're going to take our acid, which is HCl, hydrogen chloride, or hydrochloric acid, and we're going to pour out 25 milliliters into this graduated cylinder. And when you do it, you want to find the meniscus, which is at the lowest curve in the graduated cylinder. So it's a little bit high. Let me see. Actually, you want to get as level as possible, and then look, and it's actually right at 25 milliliters. So this is perfect. This is what we want. So we're going to take this, and we're going to put it in our flask, our Erlenmeyer flask right here. Put that all in there. And then now, what we're going to do is we're going to take our sodium hydroxide. So this is going to be our base. So pretty much what we're trying to do is we're trying to neutralize it. And what I mean by neutralize it is, so there's a neutral point in the pH scale where it goes from 0 to 14. And the neutral point would be at 7. So we'll have our sodium chloride, which is a base. So your acids range from 0 to 6, and your bases run from 8 to 14. And so as we pour this, we're just going to get some base. It's not about a specific amount. We want to get at least 50 milliliters in our burette. And so once we add the base to the acid, then we'll be able to get it closer to an even pH. So we're going to pour this here. Make sure that it's perpendicular. So the stopper, make sure it's perpendicular with the burette so that it doesn't just drip out. Oh, spilled a little bit. All right, so I'm going to pour this in here. Like so. So we're trying to get it all the way up to 0. So we see that it's a little bit above it. We want to be as precise as possible within reason. And so we see that meniscus is a little too high. And so it dropped a little low right here. So we're going to try it again. It didn't take too many tries to get it right. All right. So now we're going to continue to try to get it even and to have your burette at 0 so that we have an accurate starting point. So we're just going to purge some of it. All right, so yeah, now my meniscus is at 0 for the burette, and we're going to have that so we can know how many milliliters it takes for our acid to change colors. So we're gonna add some phenolphthalein, and we're gonna add 3 drops of it. And this is an indicator. So this will pretty much tell us when the acid becomes neutral or at a 7 pH. So and we're going, and our data collection aspect is going to be determined by our volume that it takes in order to get this base into this acid to make it neutral. So we have our acid right here, and we're trying to see at what point it will become neutral. So as we begin to allow some of the base to get in, you kind of just let it go. But as you see pink beginning to form, you want to slow down so that you can get it at the most accurate points. So we see a little bit of pink starting to form. So you want to go, and then we want to slow down a little bit. And then make sure that pink runs out. So we want to continue to titrate until the pink comes and it stays. So as we do it, we want to mix it around. And the reason we mix it around is because we want to make sure that the base the titrant that we have, that is the base, we want to make sure that it's spread evenly throughout the solution. So do that. Mix it around. So right now we're at about 16.5 milliliters. Continue to see it. This part is kind of tedious, but it'll get us we want to be as accurate as we can be. Oh, we're getting pretty close. We're currently at a little bit past 19. Let's see, we're almost there. Doesn't want to go all the way neutral, but we're gonna get there in a second. This might be it. Alright, here we go. So we see it staying pink. And so at this point, it is at 21.6. 21.6 milliliters is how much it took. So milliliters, and this is of NaOH. Okay, so we have this. This is what we were looking to find, and we were able to find that. So we're going to use the molarity equation in order to determine moles. So with any substitution double displacement reaction that we see, we can only compare moles. You can't compare grams or anything like that. You have to be able to compare moles because we're trying to find the molarity of the HCl. So if we have the volume of the NaOH, we need to be able to use the molarity of the NaOH, which is given to us. So the molarity of the NaOH is, yes, you can see it right there, 0.1170 molarity of NaOH. So if the formula is M equals N over L, you want to get the N on one side because we're trying to find the moles. So you multiply both sides by L. So L times M equals your moles. So, like I said, it has to be in liters, not milliliters. So you want to convert that. So that will become 0.0216 liters times 0.1170 molar. And this will give you your. So we were trying to calculate the number of moles of NaOH through using the molarity formula. So we multiplied the liters times the molarity, and that would give us the total moles of NaOH. But we're trying to find the molarity of HCl. So we'll have to use mole ratios as we go to our equation. And since it's a 1-to-1 ratio between the HCl and NaOH, given that the NaOH is 0.00252 moles, this would be the same amount of moles in this equation. So, given that information, we can use that to calculate the molarity of the HCl. So, we have our 0.00252. Do you remember our equation is M equals N over L? So that's our moles of HCl. Then we're going to divide that by 0.025 liters. Because this is from our 25 milliliters. We have to use our initial HCl volume and not the total because we're trying to find the original molarity of the solution that we were given. So if you divide this out and calculate it, you would end up with 0.1008 molar. And this would be our final answer to calculate the molarity of the HCl. And we're able to check this because the solution that we put in was 0.1 molar HCl. So this, what it actually is, and the answer that we were able to calculate was very accurate. And we can continue to do this. If we ever have an unknown acid, then we could add NaOH, look at the volume of it as we did, but we found the volume. Then we use the volume times the molarity in order to find the moles, compare our mole ratio with our equation, use those moles divided by the volume of the original acid, and be able to calculate the molarity of that acid. And this is how you would do an acid-base titration neutralization.